Welcome to Moldflow versus Moldfloor. I am Jennifer Schmidt, and I am the Senior Moldflow Instructor at the AIM Institute.
And I'm Jason Travitz, the Senior Processing Instructor.
And in front of you, you have a pressure plot from Moldflow. This would represent the system pressure for this part. And I'm getting a pressure prediction of 16,162 PSI. Jason has given me a transfer pressure off the shop floor of 16,625 PSI. And what I would ask is, if you think among yourself, is this result close enough that you would consider this a success? And while you're thinking on that, the one thing I might point out is, what are we missing from the simulation? And the one thing that's not always done, can't always be done unless you have that kind of information, is adding the machine nozzle in. We're only predicting what we've modeled, and what we haven't modeled in this case is the machine nozzle. So in this case, the Moldflow results do not match real world. And in fact, we're probably over predicting pressure.
Yeah, one thing I'll mention, when I did this for full time, we would actually model up the standard set of nozzles that we had available for all of our molding machines so that the analysts could include those per our specification in the analysis. And so we had a good idea of what that would be in the prediction. So that is one option. You just have to know what your available nozzle is. In our case, we standardized those and blueprinted them and then provided the designs. This is our Moldflow to Moldfloor, if you want to call it a worksheet. I teach all of our molders here through our molder series in our advanced classes to use this sheet and this workflow. So what this is we see two columns here basically. We've got a Moldflow column and a Moldfloor. So when the analyst presents the results to our people here, they'll actually be able to go down through each one of these variables and record what the output was out of Moldflow. Now they'll do that after we actually train them on Moldflow, basically Moldflow understanding and interpreting results. So Jen teaches all the molders here how to understand the reports, provides the reports to them, and then in class or in a meeting like we would do in the real world, they'll go through. So you'll see things like fill time, which we're going to talk about here in a little bit, melt temperature, the mold temperature, VP switchover, pressure at VP switchover. So we would go down through and record each one of those that was predicted by the analyst. Now we do teach from the Moldfloor side to use a trust but verify methodology. So they'll use this, take this under advisement, go out to the floor, build their process using the appropriate process development methodology, and then upon the completion of developing a process, they'll record all of their information from the Moldfloor. We then initiate a second meeting where we sit down with the analyst, provide all of the results of what was actually done on the Moldfloor, how we developed that process, what settings we chose and the results, so we can bring the loop back around for an after action report and discuss any differences, maybe where there was opportunities to improve in the future, things we learned, all those sorts of things. So we really want to encourage this back and forth interaction. And even better, if we can get involved up front, we can make sure we, being the molder, gets involved up front. We can actually agree to some of the inputs that we're going to do during Moldflow. That way we start off both in the same place. There's a second page here. You'll see we get into second stage. So here we have hold pressure, hold time and gate seal, clamp tonnage, the flow rate that's required, and cycle time. So we have a lot of good information here to pass back and forth, and these conversations are beneficial to really improve the quality of this event.
So the first topic we're going to cover is melt temperature. This is the screen I would see in Moldflow as the analyst. And we'll highlight a couple things. The first being that default melt temperature, that 527, that comes from a mid-range temperature that's taken from that min to max melt temperature range. Now, the thing to watch out for is, although the nomenclature would suggest it, it's not always the material manufacturer's recommended ranges. So we would caution people to compare this against material manufacturers' data sheets. And if we do that and pull up this specific material, you'll see that that default temperature, the one that would get fed into the process settings unless the analyst would overwrite it, of 527 is actually at the very top end of the processing range, which isn't something I'm likely going to want to start at. What we learned when we took over the material characterization lab a few years ago is that the company purchasing the characterization specifies the temperature range they want to use. So that nomenclature is a little bit misleading. Now, a lot of times it is actually the same ranges, but you have to watch out for when it's not.
And I would add here that from the processing side, where does the processor typically start with a melt temperature? We teach here in class, don't use any more temperature than you need. It's energy in and versus energy out. But the hotter that we make a melt to fill a mold, that's just more energy we need to take out. Now, certainly if we need that to make a good part, to achieve an acceptable fill pressure, to get thin features to fill because of hesitation, for whatever reason, if we need that melt temperature, then certainly by all means use it. But rather than starting at a midpoint or the high end, why not start at the low end and work your way up as necessary? It's funny when we ask processors that tend to start in the middle, why do you start in the middle? Well, it's in the middle. And then we ask, well, have you ever reduced the melt temperature to see if you could fill the mold with a lower melt temperature? And usually we get a puzzled look and a smile that they've never done that. So if they were following that approach, we would basically be at the opposite ends of the spectrum here. The processor would be starting out at the low end, only increasing temperature as they needed to make a good part. And they certainly may start scratching their head when they see a simulation coming to them with something that's saying run it right out of the gate at a high end of the melt temperature, unless there's a good reason for it, especially a material that may undergo degradation or be thermally sensitive. Here we have measuring the melt temperature. So this is really coming from the Moldfloor side. I've had a lot of discussions back and forth in these meetings and exchanging this information where we would always provide a melt temperature back and forth. Wanted to draw that to everyone's attention. How you take the melt temperature can have a significant influence over the reading that you get, which you end up telling the analyst the melt temperature was versus what it really was. So here what you see on the right is some data that comes from our PT program. We essentially take students out every time from our class. We've got probably 20 classes worth of data here that we can look at. And we give them 4 different melt temperature measurements and ask them to take a series of measurements on the same process running in the same machine with the same material, basically set it up the same way every time, and they go out and take a series of melt temperature measurements. The equipment that we give them is number 1 here. The red bar is an O20 thermocouple, just a simple thermocouple plugged into a temperature unit. We have a fast-acting probe, which is pretty commonly used in the industry. It's about an 1/8" probe that they would use under the guise of being fast-acting. We also have an IR laser gun, which is going to take a surface temperature measurement. Those are the generally relatively inexpensive laser guns that you may have on the floor. And you can also have an IR camera. You could be looking at a several $1,000 IR camera. In this case, this data is from one of our instructor, John Bazzelli's FLIR, high-end FLIR thermal imaging camera. And a couple of things to draw your attention to here. First of all, each one of those units, even though we're measuring the same melt out of the same process, is giving us different temperature readings. Not only do we get different temperature readings, but we have different ranges. So if we just compare the grossest differences here, you can see the O20 thermocouple gets a reading of over 415 degrees versus that melt probe of 390. That's 25 degrees difference right there out of the gate, plus 25 plus degrees difference. So I could be reporting a significantly different temperature to the analyst than what I actually ran, and it may confound some of our differences between the Moldfloor and Moldflow. Also, there's quite a bit of range with the melt probes. They just seem to be very inconsistent. There's a large thermal mass. It takes time for them to warm up, which actually ends up looking like a colder melt temperature. Laser guns, if you know anything about laser guns, are taking pictures of the image or the surface of the material, which tends to skin over. It cools quickly as soon as it hits the air. Same thing with the IR camera, although it is giving us a much better reading. And interestingly enough, we can actually close the gap between the red bar number 1 for the thermocouple and the blue bar number 4 if we take an image of the stream of plastic with the IR camera. So when John did that, he gets almost an identical measurement. So this should give you an idea how this could play out in the real world. Here we have, I was running a process. This was for a material that we had, a PCABS material that we had in-house here. We had run analysis on it. We were out running parts, and it was characterized in-house, so it was a very controlled experiment. We had Jen run the analysis. I went out and ran the parts. I immersed a 125 melt probe, the fast-acting probe in. I got a 483 Fahrenheit melt temperature. Then I took the same temperature, or took temperature of the same melt out of the machine with an 020 thermocouple, and I got 525. So what do we have there? Nearly 40 degrees difference. Now, if I was to feed that information to the analyst, in this case, we've got the Moldfloor, that is the pressure at transfer with the nozzle pressure losses removed. So we compare that to a Moldflow that was run at 483 F, predicting a couple thousand above, versus a Moldflow run at 525 F, in this case, 3,000 plus PSI less. So something as simple as how I report the melt temperature, or how I try and match the melt temperature, depending on whether we're going from the Moldflow to the Moldfloor or the Moldfloor to the Moldflow, we can really start to skew our results here, because the melt temperature is not actually what we think it is, depending on how we measure it.
So topic number 2 that we're going to cover is going to be plastic flow rate. I have this slide, which is a reference slide from a previous summit, 2018. We've covered this in more depth, so if anyone wanted to hear a more in-depth version of this, you could go to those recordings. But basically, to sum it up, there are various ways to try and figure out a fill time within Moldflow if you're an analyst. And depending on the method you use, you can get kind of wildly different results, probably also depending on the application. My preferred method would be the DOE method, and if you're in the top 2 tiers of Moldflow Insight, you would have ability to do this. Otherwise, similar to the previous slide, you could just run multiple studies at various fill times and then plot it through Excel. But both are kind of attacking this in a what I would call a fill time scan way. We are basically looking at injection pressures versus various fill times and plotting that pressure curve. And this gives me a sense of what my optimum processing window should be. And on this particular application, this is our next gen part. We like to use this for training purposes and R&D. We're already somewhat high pressure, so I would probably stick a little bit closer to the bottom of that curve, maybe in the 3/4 second to a second fill time. If we look at the Moldflow on this, at 1 second, the tabs will short. I can run multiple studies at various fill times, and I can tell Jason that he needs to run this at 0.4 seconds or faster to get those tabs to fill. And then if we compare that to actual parts, at 1 second with this particular material, those tabs do indeed short. But the cosmetics on the part look rather nice. At 0.4 seconds, those tabs do fill. Moldflow was pretty dead on with those time ranges of where the tabs short versus where they don't. But now at 0.4 seconds, you can see there's some cosmetic issues in this part. And while on this particular analysis, there wasn't anything to prompt me to tell Jason that we would see cosmetic issues, I'm not exactly surprised to see them, but I wouldn't have had anything definitive to point to towards that.
So as a processor, we would use the trust but verify approach. Jen's provided some beneficial information here. She's showing us in her predictions that at the slower fill time, the 1 second fill time, we should expect some a short fill, or in this case, it's really a hesitation. Those tabs are maybe about 1/4 the thickness of the main body of the part. They tend to hesitate, so we know to look out for that. But I'm still going to go through my version of a fill time scan to determine, what the part wants for the optimum plastic flow rate here. So what you're looking at to get you oriented, we plot pressure in the vertical axis and fill time in the horizontal axis. With the far left, the 6.615, that picture with a very nice surface finish in the lower left-hand corner, that's at a very slow fill speed. As we progress to the right, we are increasing the fill speed, so the fill time is dropping, and as we go up on the vertical axis, we are increasing in pressure. So we go through, we first start producing a 95 to 99% full part in the fullest cavity. We mark that as our master sample and record the pressure and fill time to do so. Then we subsequently step down the injection speed or injection rate, depending on what kind of machine we're running on, while recording that pressure and fill time. Now, the one key thing that we do here, the one key step, is that we will adjust cutoff position each step of the way so that we make the same fill-only part every time we make a speed change. So as we slow down, we tend to have less inertia in the screw during injection, so we have less over travel, less material results in the cavity, so we'll actually lower cutoff position. We'll maintain at each one of these speeds. If we were to look at that cavity 2A, it would look exactly the same. What that provides for us is a fill-only shot at each speed so we can evaluate the cosmetics, the part filling, any kind of part feedback, as well as the true pressure it took to make that shot. So you can see here we plotted it out. We first liked the cosmetics better at that slower speed, but as Jen warned us here, we were unable to fill those tabs that are hesitating. So we went to a faster injection speed, compromised some on the cosmetics. Once again, we were unable to fill the tabs. We also tried to transfer what we call transferring the outside cavity. We're essentially trying to fill the cavities fuller on first stage. That still didn't work. So we ended up at the selected speed, which is in the far right corner there. In order to get the tabs to fill, like Jen had stated, we were at about a 0.6 second fill time here in order to be able to fill those tabs. Cosmetics are poor, and we've passed above our 80% threshold, 80% of the max available injection pressure on the machine. So we noted here the poor cosmetics. We noted the risk of running pressure limited because we are above that 80% threshold. And we also made notes to talk to PD, product design, about the cosmetics as well as operations to look at whether we should run it in this press or not. So it's very important that we document this. This can then go back to the analyst along with the parts. We can sit down. This is part of our document and explain, and if necessary, defend what we did. But here we've used what the analyst has given us, made the best of that, and collected our own information and settled on a fill time, but it's very easy to transfer back and forth. The other thing that we get at the same time that we basically get for free is we get the ability to look at how does the machine do during each one of these injection speeds. How is it doing its set speed versus its actual speed? So some people would refer to this as linearity or injection speed linearity, machine linearity. I'm just referring to it as machine set versus actual velocity. To get you oriented, the easiest way to look at this, the blue bar is the set for each one of the speeds, 1 through 12. The blue bar is the setting. The red bar is the actual speed. So the closer they are together, the less the error. So you'll see that error on the right. We may start with a 6% error, working our way down to where we're basically 0 error. So the machine on the left is good. If you look a little closer to the machine on the right, you'll notice that those red bars really tend to stall out over here at the higher speeds. And I did a little blow up for you to see. You can see we set this machine 5.57 cubic inches a second as the max speed of that machine. And then we stepped down in 0.5 increments. What you notice is the fill time barely changed. That's because the machine, even though it has the ability to set it up at 5.57, and that's what the specs claim, this machine really can't go any faster than 3.5 cubic inches a second. This is an important piece of information from the Moldfloor that we need to provide to Moldflow. I need to let the analyst know here, let Jen know that I can't get 5.57 out of this machine, that 3.5 is probably the max. And then she should consider that when she's doing those previous studies she just mentioned. I've gotten burned on this before because I provided the machine specs here on the left, and in reality, the machine can only do what it can actually do here on the right. The analyst found a fill time, and we did a lot of work with those predictions based on a fill time that I couldn't achieve because of the machine performance. So this is good information to provide from Moldfloor to Moldflow.
So the third topic we can talk about is material characterization. And similar to all these topics, we could talk about this for the entire time. And in fact, we have done a previous summit recording on this one as well, I think back in 2017. So again, more details in that one. But a quick overview is that Moldflow gives us these different quality indicators or different levels of characterization. They try and break it down into a gold, silver, bronze, so you have a quick idea of how well that material is characterized. And those characterizations or those quality indicators are based on the lab that tests it, the type of data that's available, the type of testing that was done, and then the age of the testing, if it was tested more recently or if it's, 10, 20 years old. Those things expire after a set time. So gold-rated resins should give you a lot more confidence in the data that's coming out. Bronze-rated resins tend to be a lot of supplemental, family averaged data. Can still be used, but with a little bit more caution, perhaps. Now, this is something that is of a particular interest to me. So for another class, I'd taken 6 different characterizations of the same grade of polycarbonate, found it in the database a number of different ways. Some were different testing facilities to material manufacturer versus a couple different labs. Some were older versus something that was done as recently as a year ago. And these range between the bronze and the gold quality indicators. It's important to note here that while the mesh type will change, the mesh density is identical, so that shouldn't be a factor. The only thing we're really changing here is the mesh type of the part in one instance. Mainly this particular bar graph, everything was a 3D part, and then we really just changed whether those runners were modeled in beams or 3D tetrahedrals. So what you're seeing in this bar graph is the 6 different characterizations of that polycarbonate with the pressure predictions for both beams and 3D runners. And you can see, based on these 12 studies, you can get a wide range of pressure predictions. I'm going to show you the min to the max because I think that's the most interesting. So the minimum pressure I saw doing this was just around 10,000 PSI. The max pressure came in at right around 26,000 PSI. That is a big difference in pressure depending on what I'm trying to do with this, right? If I was trying to size runners, I could put my customer into a pressure limited position if I didn't pick the right material going forward. Just for curiosity's sake, that 10,000 PSI prediction happened to be a bronze rated resin. So again, a lot of family average, a lot of supplemental data. That 26,000 PSI pressure prediction was a gold-rated resin that was tested within the last year. So I have a lot more confidence in that particular one. I'm going to take that particular characterization, and then I'm going to take the rest of the characterizations out of it, and now just look at mesh type. So this is that gold-rated, very recently tested version of that polycarbonate. The pressure prediction on the left is a 3D part, but the runner is meshed with beams. In the middle, we have a dual domain part with beam runners, and then on the right, we have a 3D part with 3D runners. All same processing, all same mesh density, it's just the mesh type that's varying. And even within this, you'll see nearly an 8,000 PSI swing. So those decisions that an analyst is making up front can have a big impact on how accurate we are when we're comparing this to the real world. So that would be the number one question, right? How does this compare to the real world? I'm going to stick with my 3D part and 3D runner. That is somewhat my preference typically to use, though there are reasons to go another route. And Jason can give me a transfer pressure off the Moldfloor. And that transfer pressure is 35,000 and some change PSI. Now, that on the surface doesn't look like a great comparison, but again, what you have to remember is there are machine losses, screw conveyance losses, and when we take that out, we get a system pressure of 27,389 PSI. This would be a fair pressure to go ahead and compare against my Moldflow results, and while it's not dead on, this is very, very close considering.
I'd add one more thing here. Some of you that may have seen pressure losses out of a machine from a pressure drop study or something, which we'll speak more about at the end, may think 8,000 is quite high. Commonly, that I would agree in a reciprocating screw molding machine. However, this particular machine happens to have a long nozzle adapter on, so we frequently will see pressure drops anywhere from 6,000 to 10,000 PSI just to get material out of the molding machine nozzle under the process conditions. So we only know what that is when we get it from the floor. So that's something that should be part of your Moldfloor process sheet, is actually an air shot. They should be taking that. I would more commonly expect to see that probably in the 2,000 to 3,000 PSI range in my typical 1/8 inch, 1/8 inch, 3/8 inch nozzle, something like that. But I don't know unless I get it. The one other note I'll make, and we don't have a slide for it here, but how they take that pressure loss out of the nozzle is very important. Many machines don't purge into the air under the same conditions in which they inject into the mold. They may have purge settings, reduced velocity for safety or something. That will not give you an accurate screw conveyance and air shot pressure. So the machine needs to be set up to inject into the air under the exact same conditions, speed, pressures, everything that it would inject into the mold in order to get an accurate number there. This item here, machine response, is something that we spent some more time on looking at currently. I'm going to get you oriented a little bit of what I'm referring to. I think there's an opportunity here for Moldfloor and Moldflow to work together to better understand what's really going on, and have a couple examples to drive home the point. So just to get you oriented, in case some folks aren't used to looking at some of this data and graphs, here's my home drawn in Adobe Photoshop, what we would call a cycle graph. So to get you oriented here, you have time across the bottom in seconds. So think of that as a 17 or maybe 20-second cycle. This may not be an entire cycle. In the vertical axis for 3 of the curves is pressure and PSI. And then we also have a screw stroke curve that's in volume cubic inches. Okay, to identify these curves, we have the red curve is the injection pressure. So we see a relatively sharp peak there. That's the pressure to fill the part. Then we're going to see it drop down into pack and hold, our second stage, and then go into screw delay and screw recovery. We also have the stroke volume. So here we can see a very linear injection stroke. That would represent the rate at which the screw is moving, the volumetric rate. It's a good linear stroke. All right. Then that's going to result in inside the cavity, we're going to see cavity pressure at the post gate location, so just after the gate, and then the end of cavity pressure. So we're laying down those pressure traces and that stroke volume over time. All right. What I want to key in on here in machine response occurs after the transfer from fill to pack and hold. So fill is a velocity controlled stage. We use whatever pressure is necessary to fill, but how that machine transitions from V to P, velocity to pressure in second stage, can significantly impact how we pack out the part. So the area that we're keying in on here is what we refer to as machine response, what I've highlighted in that box. How quickly does it get from that sharp peak that it was velocity controlled down to whatever the motor has set it to do for its pack and hold pressure? That's going to be the result of machine tuning, pack speed setting. So you can limit or set the amount of speed that you allow the screw to move it to generate the packing pressure. And then there's also response modes or functions, one of which I'm going to show you here in a minute. But how that machine behaves, how quickly it bleeds off that pressure and reaches a stable pressure here, is going to affect how we pack that cavity. And in some cases, even how much we pack that cavity. So packing rate, really the slope of those two curves, the green and the blue curve on the front side, as well as the resulting peak cavity pressure. So you can think about, you could have an instance where you packed it very quickly at a very high pressure, or you could actually pack it slower at a lower pressure. And that's all going to be in terms of how this machine responds. So I have some real-world curves here to show you what that would look like. So here we have our Sodic molding machine. We're running a 6-second pack and hold time, and we're using 14,000 PSI of pack and hold pressure. It does take quite a bit to pack out some of the features in this part, okay? So you're going to see your injection pressure curve, your post-gate curve, and your end of cavity pressure curve here. To get you oriented again, we're going to focus on the area of this injection pressure curve from the machine after fill. So the transfer from fill to pack and hold. Really, how does it behave in this region? So we've got that 14,000 PSI, and I made a note here, pressure drop time 0. That's this setting right here. That's one of those features of the machine that you can control the machine response. That then results in this peak cavity pressure. So you can see we have a little over 8,000 post-gate and about 7,500 at the end of cavity. Now, something as simple as the person coming in and changing that PDT. Maybe they know what this is, maybe they don't know what it is. You know, there are reasons for having these features. It can be beneficial to pack apart differently depending on, you know, thin features, trying to pack at the end of the fill. Maybe you want to try and pack the part more gently. It just depends on what you're trying to accomplish. So there are reasons for having these features, but let's say we put a 0.5 value in this PDT, not a huge value. So once we get from transfer, from fill to pack and hold, you'll notice quite a bit of difference in that curve. It doesn't drop off as sharply. It doesn't reach set point until sometime quite later than before, okay? I currently have the pack pressure here only set to 7,000 PSI because I want to drive home a point. So we went from 14,000 to 7,000 PSI, but I put this 0.5 value in here, and you'll see I have almost identical end of cavity pressure. So I have to be careful. If Jen doesn't have this information, doesn't know how this machine is responding, she's not going to capture in her analysis this additional packing that's occurring because it takes such a long time for the machine response to happen that you're actually packing at a higher pressure initially. And this can be both under pressure or over pressure. This would be what we call over damped. Okay. Most times an analyst is just going to get a pack time and a pack and hold pressure, or a molder is just going to put in a pack time and a pack pressure here, and they may or may not even know what this is doing. But something as simple here is double the hold pressure generated really the same conditions in the cavity. So I brought those back from the previous slide to show you we're basically looking at about the same thing. Now, some of you may be thinking, well, what would have happened if I'd have kept the 14,000 and put this 0.5 in here? Well, I didn't want to find out because when I started to increase the pressure, I started to flash the tool and didn't want to damage something. But I did get up to 11,000 PSI. I used a pressure drop time of 0.5 with the 11,000 PSI. What you'll see here is, once again, that over damped condition, a higher pressure for a longer period of time during pack and hold. And at no point in here am I actually getting the pack and hold pressure I desire. That doesn't occur until out here. And what we saw, the resulting cavity pressure was over 9,000 PSI. So you can start to see there can very easily be some miscommunication between either taking the Moldflow results to the Moldfloor or taking the Moldfloor process settings back to Moldflow in order to see why maybe there's a disconnect in predictions or something. Something as simple as this machine response can create those sorts of things. And these are frequently, I see a lot of molders and I see a lot of these features on machines frequently are not very well understood to the point where if you don't have this data to look at, the only way to really see this is if you have a data acquisition box on your machine, or if you have a newer machine where you have a machine controller, you can see this injection response. And you can't see inside the cavity at all if you don't have cavity pressure sensors. That would require some sort of cavity pressure sensors. We're currently working now to look at how we can translate these back and forth. We believe we can export these response curves from some of our data acquisition. So we're going to continue to work on that and even look at the difference in predictions with running these different response modes. So there are some other considerations that we have. One that warrants a little bit more mentioning in detail is the pressure drop study. I will go over this at a high level here in case some of you aren't familiar with it. If you do want more information, I did a much more elaborate explanation of this in the 2018 summit. You can refer back to that recording, which is available online, where I get into this at a greater depth. But one of the places where there's a lot of discussion back and forth between Moldfloor and Moldflow is the pressure drop study. So what I'm referring to here, if you look on the left-hand side, would be state of the industry or kind of standard accepted practice, where the molder would make a series of short shots making a 95 to 99% full part, making a part that plastic is just after the gate, making a part or making a shot that's just before the gate, and collecting the pressures at each step. So that step back method provides a pressure loss to fill the runner, a pressure loss to flow through the gate, and a pressure loss to fill the part. Molder will typically do this if they're pressure limited. They're trying to look for where they can reduce the pressure in the flow path. So in this case, they may conclude that they could take a significant amount of pressure out of filling this mold if they were to, say, increase the runner diameter or open the gate. Many times we want to verify those results, so we kick that over to simulation. We say, hey, can you check out what I'm thinking here? Simulation comes back and says, okay, maybe the runner, but not the gate. There can be a lot of back and forth here. We can also provide this information from the shop floor, the mold floor, to the analyst and tell them, go back and figure out why you didn't predict what I'm getting. And I was very much guilty of being a person from the floor who always believed that what comes off the floor is the real world and what comes out of simulation is coming from a computer model. But what we did here, the focus of our study was we did the methodology on the right, the instrumented mold method. So by putting a series of sensors throughout the flow path, we could take the pressure when the part was 95 to 99% full, just like you would do in your analysis by putting nodes in as are shown in that center simulation method. What we found was, in this case, the pressure distribution was much different than we had originally believed using that shop floor method. It was much higher in the runner and lower in the gate and part. So in this case, we may have incorrectly concluded that we could reduce pressure by opening the gate. This led us to compare the methods all together. We concluded that the instrumented method is the most accurate. So in this case, simulation does a good job of the trend, not necessarily the magnitude, but we've already mentioned a number of reasons why things can be different on the magnitude side. So there's still probably work to be done there, but certainly does a better job of capturing the trend correctly. And what this amounts to, and why you may want to go back and look at the previous presentation from 2018, or even read an article that John Beaumont wrote in the SPE magazine, is that we're not accurately capturing the frozen layer development by stepping back the flow path. Okay, so if you look at these two images on the bottom here, and you can even go into simulation and watch this grow, the frozen layer grow as the mold fills. So imagine only making, say, a runner here on the left. The frozen layer thickness is rather small, but as the plastic continues to flow through the runner system and into the part, that frozen layer is growing. So the only way to truly capture the pressure loss through, say, the sprue, the runner, or even the gates is to actually make that complete fill-only part, so that we can allow that frozen layer to develop. Then we've captured the pressure through the entire flow path. The step-back method doesn't capture that. So we have to be very careful there. It can be misleading. So in this case, we would tend to believe, especially in the trend here with simulation, the instrumented method isn't very realistic to do in the real world, but certainly was good to understand this and understand how that frozen layer development impacts what is pretty commonly accepted study that can be used to make significant tool change decisions, or worse yet, given to an analyst and told to go correct their predictions based on the information they were given, which may be skewed or incorrect. So the kind of catch-all here at the end is, what about everything else? We talk about all of the different things that could really factor into this, and they lie in all different arenas. They could be in the simulation, they could be in the material, they could be in the processing. We didn't talk about a number of things even from the mold floor side that can skew things. Something like melt temperature. We tend to give you a melt temperature, you the analyst, the melt temperature from the mold floor that's really the highest laminate we measured. That's not a bulk temperature. Just in that case, it may be better if we could come up with a method to get you a bulk temperature measurement versus a highest laminate temperature, things like that. So a lot of things to consider, but it all begins with a dialogue back and forth. So how do we work together to make this work from the mold floor and mold flow side? First of all, we have to collaborate. It's important that we have upfront communication and clear objectives. We need to discuss what we're going to use for our inputs and what we want to accomplish with the analysis. The analyst needs to understand the capabilities. Things like the max flow rate, injection pressure, clamp tonnage capabilities of the machine. Many times they're given published specifications, but what the machines are actually capable of are not the same thing. So if I know something from the Moldfloor side in terms of max flow rate capabilities of a molding machine, I need to convey that to the analyst so they can accurately analyze only the usable range of the machine. We need to understand water flow capabilities. We never want them to simulate something that we're not capable of replicating on the floor. We discussed agreeing on analysis inputs. I used to do this in the form of a request form. This works very well for everybody to be on the same page. As the Moldfloor representative, I would actually submit this with the parameters that we wanted to run along with what my objectives were. We can agree to that up front, make sure everybody understands what we're trying to accomplish, and proceed with that understanding. One of the biggest things here is understand the capabilities and limitations both of the Moldflow and the Moldfloor. There's only so many things each can do. It's important that we understand those. I can only give you the highest melt temperature from the Moldfloor, for example. And then there's obviously limitations on the Moldflow side. So understanding those and doing our best to make all of those work. We need to review the results before process development. This should not be a siloed activity. This should not be done and never make it back to the floor. It's important to sit down with the folks on the Moldfloor that are going to be running the parts and review with them the results, what we found. They're going to be able to use that as starting points. It gives them a head start, a heads up on anything they might need to expect happening when they go to run the tool. From the Moldfloor side, we're going to trust but verify. We're not going to follow these things blindly, but we should be on the same page from the beginning because we started with a request form. We agreed to clear objectives. We've been communicating throughout the process. When we go out to run, we're going to do a trust but verify. We'll use the ranges, say for flow rate. We'll take into consideration the predicted gate seal time, any type of potential issues that were pointed out in the Moldflow. We'll take those all under advisement work, creating the process. We'll use those outputs whenever possible, but we're going to verify that we see the same results and note anything that's unusual. Once we're done on the Moldfloor, we're going to document the process outputs, including the equipment and methodology. Very important that if I provide information from the Moldfloor to the Moldfloor person, that I explain exactly how I got that. It's not enough to simply say I got a melt temperature, but how did I take it? Where did it come from? Where did I get these outputs from the process? And report them as accurately as I can, especially given some of the items that we pointed out earlier. And we want to be very careful when we resolve any discrepancies between Moldflow and Moldfloor. In the past, I would have went in as a Moldfloor representative directly to the analyst and said, clearly you need to improve what you're predicting here because it doesn't match what I'm seeing on the floor. We've pointed out in several cases here where I could have been giving that analyst less than accurate information in terms of melt temperature, pressure drop, some of those things. So very important that we work together, we understand those differences and determine how to best move forward, increasing the accuracy of our predictions, as well as the accuracy of reporting the actual Moldfloor results. We'd like to thank you for attending. Here's our contact information. We're happy to field any questions you may have if you'd like to reach out to us through email or phone, and we'll be available here at the end of the presentation to answer some questions. Thank you.